Yeah, good morning, students. Now we are going to discuss about the stability of a control system. Here, the main important topic is root average criteria. With the help of this root average criteria, we can decide the type of stability by using some array. So it determines the nature of roots in the S plane of a control system without analyzing the complete system. The Routh-Hurwitz criteria stability criteria is based on ordering the coefficients of a characteristic equation. Here we are using a naught into s power n plus a1 into s power n minus 1 plus a2 into s power n minus 2 plus and so on an minus 1 with s power n 1 plus an into s power 0 is equal to 0 now, where a naught is greater than 0 into a schedule is called root array. If you observe this is the format of the formation of root array. Here we are taking s power n, s power n minus 1, s power n minus 2, s power n minus 3, and so on s cube, s square, s1, s0 as the power of s in our equation. For that we are having the corresponding factors of that power of s, a0, a2, a4, a6 is called even array, even row, a1, a3, a5, a7 are a odd row, like that. From that we need to fill the remaining power of s, like if you want to get this b1, we need to cross multiply a1 with a2 minus a3 with a0 by a1. Similarly, if you want to get b2 term, we have to get the equation like this: a1 into a4 minus a0 into a5 by a0. Similarly, for b3, a1 a6 minus a0 a7 whole by a1. From that we have to fill the remaining also. If you want to get c1, we need to have cross multiplication with b1 with a3 minus b2 with a1 by b1. Similarly, b1 with a5 minus b3 with a1 by b2. Like that, we need to fill all the all the area of this RH criteria. Here, from this we need to know some important points. Normally, the root array is having non-zero elements in the first column of root array. Using root, we should know the property of root array by using this problem. Here, they have given one example. Using root criteria, determine the stability of the system, which is represented by the characteristic equation s power 4 plus 8s cube plus 18s square plus 16s plus 5 is equal to 0. For this, we need to comment on the location of the roots of a characteristic equation. First, we need to construct the root array. As discussed in the previous slide, you need to start with the even row. So we are having the highest power of s as 4. It indicates the even number. So we need to construct initially even row. So we are having even numbers as 4, 2, and 0. So that we need to have for the s power 4 we are having only one factor. For a square we are having the factor as 18 plus 0 as we are having 5. Coming to second one, we need to construct odd row. Odd row means s cube, s power 1, like that. For s cube we are having 8 as a factor plus for s we are having 16 as a factor. So that we need to have s power 4 as 1, 18, 5, s cube with the factors 8 and 16. Coming to s cube, we are also having an equivalent, some simplification. If you have a division of this row with 8, so 8 by 8 means 1, 16 by 8 means 2. So this will be replaced with 1 and 2. Now we need to find s square row. Means s square means 1 into 18 minus 2 into 1 by 1. Similarly, we are having this value as 16. Okay, now next one, 1 into 5 minus 0 into 1 by 1. So this will be equal to 5. So the s square row will be given as 16 and 5. Similarly, for s power 1, we need to have cross multiplication with 16 into 2 minus 5 into 1 by 16. This will become as 1.7. Similarly, we need to find the s power 0 also. S power 0 means we have to get with 1.7 into 5 minus 0 into 16 by 1.7. This will be equal to 5. So in the first column of the complete row of the all elements are positive. So if you observe this one, this is the meaning for first column of the given row array. In this case, there is no sign change in the all the powers of s. So this will be purely positive values. So the system is said to be stable, and the roots are lying on the left part of the left side of the s plane. So this is the way to determine the stability of the any system. In this case, we need to have some conditions. Those are first condition. If there is no sign change in the first column, and if there is a no row with all zeros, then all the rows are lying on the left part of the S plane, and the system is said to be stable. Coming to second condition, if there are sign changes in the first column and there is no row with all zeros, then the sum of the roots are lying on the right half of this S plane, and the system is said to be unstable. Number of sign changes is equal to here number of roots lying on the right part of the S plane. Coming to third one, if there is a row of all zeros and there is no sign change in the first column, then there is a and then there is a possibility of roots lying on imaginary axis. The system is said to be now limitedly or marginally stable. So these three are the main conditions for the stability finding by using Routh-Hurwitz criteria. Here we will see with example. Determine the stability of a closed loop system whose overflow transfer function is given by 10 by s plus 1 into 5s plus 1 by using Routh criteria. Here they have given overflow transfer function as g of s into h of s equal to 10 by s plus 1 into 5s plus 1. But according to our characteristic equation, we need to get closed loop transfer function. For that, we need to write 1 plus g of s into h of s is equal to now 0. So that 1 plus 10 by s plus 1 into 5s plus 1 also now equal to 0. From this we are having s plus 1 into 5s plus 1 plus 10 is equal to 0. By taking this product, we are having 5s square plus 6x plus 11 is equal to 0. Now we need to construct Routh array with the power starting with square, next 0, next odd, like this. So if you want to get the row of even number, you should take a square. For this a square we are having factor as 5, and last one is 11. Coming to odd one, we are having only one s, that is equal to 6. After that we need to get the s40 also. S40 means 6 into 11 minus 0 into 5 by 6, which will be equal to 11. Now if you observe the first column of the given array, there is no sign changes, but all are positive values. So the roots are lying on the left side of the S plane. The system is said to be stable. Coming to next one, row of algebras. If you construct the Routh array and determine the stability of this system whose characteristic equation is s46 plus 2s5 plus 8s4 plus 12s cube plus 20s square plus 16s plus 16 is equal to 0. For this equation, we need to determine number of roots lying on the right side of the s plane, left side of the s plane, and on the imaginary axis. He has given the equation like this: s46 2s5 to 8s4 plus 12s cube 20s square plus 16s plus 16 is equal to 0. For this, we need to construct the Routh array like this. If you observe this one, there is no sign change in the first column of the given array. Here we are having one beautiful condition, that is called, if you observe this s cube, this row will be filling with all zeros. So we need to go for auxiliary equation is equal to, we are taking it as the previous values. S4 4, a is equal to s4 4 plus 6s square plus 8s 8, and differentiating this with respect to a with s. Now we are having dA by ds is equal to 4s cube plus 12s. From this we are having equation with s cube, and we are having 4 and 12 here. Also divided by 4. Now this will become as 1. will become as 3. Now what have to do? We need to go for the continuation of the root array. So what will come here? Any guesses? Yeah, here we need to start with again s power 3 with our roots as factors as 1 and 3 here. Now we need to find the remaining s power 2 with 3, 8, s power 1, 0.33, s power 0 with 8. Now the first column, in the first column there is no sign changes. The row with all zeros indicate the possibility of the roots on imaginary axis. Hence the system is said to be limitedly or marginally stable. In this case we need to find roots also. By taking auxiliary equation s power 4 6s square plus 8 is equal to 0, by having the roots of this equation we are getting minus 2 or minus 4. Now the roots are, we are taking it as s is equal to plus or minus minus root 2 plus or minus minus 4. So the roots are become as plus j root 2 minus j root 2 plus j2 minus j2. So the roots of the auxiliary equation are also roots of the characteristic equation. Hence the 4 roots are in the imaginary axis and the remaining roots are lying on the left side of the S plane. Last one is here the first element of the row is 0. Then what I have to do? Then construct the root array and determine the stability of the system represented by the characteristic equation 9s5 minus 20s4 plus 10s cube minus s square minus s minus 10 is equal to 0. Here we need to construct the root array based on the odd power of s. Initially 9, 10, minus 9, s4 4 means minus 20, minus 1, minus 10, s cube we are having the cross multiplication of this with these two. Now this will become as 9.55 minus 13.5, s4 means s4 2 means minus 29.3 minus 10, s power 1 means minus 16.8, s naught means minus 10. So you are having many times the sign changes are there. From here if you observe this, here initially we are having positive, second it will be become as negative, again third it will be become a positive, again it will be having minus. So 4 times we are having sign changes in the first column, so that the system is said to be unstable. 3 roots are lying on the right half of the S plane and 2 roots are lying on the left half of this S plane. So this is the way to find the roots of the given transfer function, given characteristic equation, and it is the way to determine the stability of the system.